Okay, good afternoon. Welcome to Queen Mary. And we're very pleased to have you here and to have also with us Professor Nima Arkani-Hamed from Princeton. He came all the way today to be with us for this colloquium. I was asked to say a few things on fire regulations, but it's very simple. Just look for the exits nearest to you and go for it if we need it. Hopefully not. Yeah, no, without killing anyone, but yeah, it's very simple. No, we shouldn't try. No. Well, unless you are so unhappy that you just want to leave right away. Anyway, I just wanted to say a few words on the occasion. So this week we are running a workshop in the Department of Physics and Astronomy, and it's a workshop on scattering amplitudes. And we're basically celebrating the work and the accomplishments of this collaboration SAGEX. You see our logo over there. So this is it's called an innovative training network, which was funded, which has been funded by a very large grant, 4 million euros of the European Commission. And so this involves many institutes, research institutes and universities in Europe. So in Austria, Denmark, France, Germany, Ireland, Switzerland, and the United Kingdom. And also the US, and also private companies in the same countries, and also in Canada. And what unites us in this network is the interest and passion for fundamental physics, and in particular for scattering amplitudes of elementary particles, which are important objects for collider physics, for gravitational waves, and many other things. And Nima will tell us many things about this. So I will let to him to explain why they are so interesting and fascinating. And also in doing this research, we have been training 15, we call them early stage researchers, so PhD students, and we're very proud of their accomplishments within SAGEX, and now they will go on and become leaders in the field. And then I think everybody knows here who is Nima, but just for the 1 or 2 people who don't, so Nima, he got his PhD in Berkeley, and then he moved to SLAC at Stanford University for a postdoctoral position. And then he went on to get professorships at Berkeley, Harvard, and finally moved in 2008 to the Institute for Advanced Study in Princeton. And I think for us, he's one of the most inspirational figures and one of the most creative theoretical physicists of our days. And this doesn't work anymore, or maybe it's me. I don't know, yeah. But he gave many important contributions to several areas of physics. For example, he introduced the concept of large extra dimensions, split supersymmetry, for people who know what supersymmetry is. And one of the last things he's been very interested in is scattering amplitudes. And now we can switch to his slides. And in the title of his colloquium, you see the words quantum mechanics, space-time, which I think are concepts which are fascinating for everyone. And I guess we are going to learn Nima's interpretation or vision for these ideas and how scattering amplitudes somehow manage to tie them together. So let's welcome Nima Arkani-Hamed.
All right, it's really, really wonderful to be here. This is my first international trip post-pandemic, so I'm especially delighted to be here in one of my very favorite cities in the world. And to talk about, as Gabriel was saying, this fascinating subject. That's fascinating because of how basic it is. It involves some of the most fundamental and basic facts about our understanding of nature. On the other hand, it connects to some rather striking and beautiful new objects in mathematics in one extreme, and is continuously connected to things that matter for describing real experiments in the real world that we see when we look outside our windows in the other extreme. And it's a completely continuously connected chain of ideas. So it's a vast subject. I'm not going to tell you about all aspects of it. I'm going to tell you about a particular angle on it that emphasizes the deep and sort of central connection between the physics and mathematics that we're going to be talking about and these very, very basic notions of space-time and quantum mechanics. And you know, the 20th century in fundamental physics really began with these two big revolutionary ideas of quantum mechanics and space-time. There's a theoretical framework that lets us talk about possible worlds that are compatible with the principles of the unification of space and time into space-time that Einstein gave us, and of quantum mechanics. This theoretical framework is known as quantum field theory, and roughly speaking, it was first established in the late 1920s, early 1930s. But we've been spending most of the time since then better and better understanding what this animal really is. One of the big milestones was finding a particular instantiation of a quantum field theory that describes everything we know about the elementary particles and their interactions in the real world. These are ideas that describe everything that we've probed and distances around 1,000 times smaller than the nucleus of the atom, 10 to the minus 17 centimeters, all the way up to the largest distance scales, the size of the observable universe, around 10, 15 billion light years. There is one basic set of ideas that spring from the principles of space-time and quantum mechanics. It turned out to be astonishingly restrictive when you ask for things, for theories to be compatible with both these ideas at the same time. But there's a specific instantiation of quantum field theory that describes everything we know about the elementary particles and their interactions in the real world. We call it the standard models of particle physics and cosmology, if you like. But the larger theoretical framework of what quantum field theory really is, we still don't fully understand. And it's a truly fascinating thing that it continues to be a source of inspiration and pushing us forward into understanding what the deeper layer of reality is. One of the reasons for studying this subject intensively is that, you know, most of the time, physics, like the rest of science, progresses as it should by sort of incremental steps that extend things that we knew previously. And that's perfectly fine and good. In fact, physics is the oldest, most mature of all the sciences. We have a spectacular understanding of the real world. We better not mess with it and throw things out left, right, and center for no reason. But every now and then, you run into a situation where something big has got to happen, that there is a reason to suspect that there's something wrong, not with the detail here or there that you're going to fix up, but with the foundational principles of the subject. And many of us think, certainly I think, that we're at one of those junctures in the development of our understanding of the subject today. And it really goes back to what these principles of space-time and quantum mechanics are really about. One of the slogans is that we actually suspect that this notion of space-time, which is just as hardwired as it could possibly be into our picture of what reality is about, that it's very likely this notion of space-time is not really there in a more correct, deeper notion, a deeper understanding of physics. So this is the slogan that many people have said: the notion of space-time is doomed. There are many thought experiments that lead you to this conclusion. Here's a very simple one. I'm a terrible artist. You'll have to tolerate that throughout the talk. This is supposed to be a magnifying glass. And so what we're going to do is we're going to take this magnifying glass and look at a little region of space and time, and we just want to look to see what's there. Just the most basic experiment. Look at the vacuum and see what's there. Now, what we learned because of quantum mechanics, though, is that to probe shorter and shorter distances, because of Heisenberg's uncertainty principle, you need higher and higher energies. Okay, that's why we have to build gigantic experiments like the Large Hadron Collider to probe the tiniest distances humans have ever probed, right? That's the huge irony. The biggest experiment we've ever made to probe the tiniest distances, exactly a reflection of this basic fact that you need higher energies to probe shorter and shorter distances. Now, in a world without gravity, no problem in principle in this way to probe arbitrarily short distances. You just ask for more and more hundreds of thousands of billions of dollars, and you, with larger and larger multinational governments, and you probe shorter and shorter distances. But in a world with gravity, something very bad happens. At some point, you put so much energy into such a tiny region of space that what happens when you put a huge amount of energy into a really tiny region of space? You collapse the region that you're looking at into a black hole, and nothing, even light, can't get out of it. So the very act of trying to see what's going on in this little region produces a black hole that makes it impossible to see what's going on in that region. This first happens at distances of around 10 to the minus 33 centimeters, times of order 10 to the minus 43 seconds. This is a famous Planck length and Planck time, and these are obscenely tiny distances. Okay, so just by contrast, the distances that are being probed at the Large Hadron Collider, 1,000 times smaller than the nucleus of the atom, are 10 to the minus 17 centimeters. Okay, so this is 16 orders of magnitude removed still from what we can directly probe with the experiment. Nonetheless, we can do this thought experiment and discover that there's no way of giving operational meaning to distances and times that are at these ludicrously tiny scales. Every time this has happened to us in physics before, where there's a notion that we can't even in principle give operational meaning to, it's meant that that notion is approximate and is not really there. It sort of emerges from more primitive ideas. In this case, it's startling because the thing that has to emerge from more primitive ideas is the notion of space and time itself. Okay? Now, where do these issues hit you in the face at order 1, at order 100%? Well, if you take the picture of the expanding universe and run it back in time, there is a moment where the curvatures in space and time are comparable to 10 to the minus 33 centimeters, 10 to the minus 43 seconds. It's what we colloquially call the Big Bang. And a lot of people ask what happened before the Big Bang, but the problem is that the words break down. We don't even know what the notion of time means near the Big Bang. Okay? So we don't even know what it means to say before the Big Bang. There are similar questions about what happens if you throw yourself into a black hole. The sort of geometry inside a black hole is a sort of an expanding universe in reverse. It's like a crunching universe. And we have a similar kind of questions. And these are situations where our theories just break down when quantum mechanics and gravity both become dominantly strong. Now, the way I laid out the problem for you might make it seem like these issues are localized to teeny tiny distances. But there's actually a more profound sense in which a notion of space and time is approximate, which doesn't necessitate going to really tiny distances, but does ask you to make very accurate measurements. One of the things that we learned from quantum mechanics is that in order to talk about precise observations in quantum mechanics, really sort of things that really make sense in quantum mechanics is famously a probabilistic theory, so you can't predict what happens next from a given experiment. But if you repeat the experiment over and over and over again, and the limit where you repeat it infinitely often, you can predict ratios, frequencies, probabilities. Okay? Another famous, less famous, but equally important fact about quantum mechanics is that if you're going to talk about any observation in quantum mechanics, it has to divide the world into two pieces: an infinite measuring apparatus that measures and interacts with a finite system that's being looked at. Why do you have to do that? Because if the measuring apparatus itself was finite, there's an irreducible amount of error associated with the fact that the measuring apparatus itself can suffer quantum mechanical fluctuations. Okay? Now, this is an extremely tiny level of error. Just to give you an example, let's say I want to measure some property. I don't know, the mass of the electron, anything you want. I'm made out of 10 to the 30 atoms. But I claim that I cannot measure any meaningful quantity to an accuracy better than 10 to the power of 10 to the 30. Okay? 10 to the power of negative 10 to the 30. Why? Because let's say I'm doing this measurement, I'm going along, ding, 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 I'm getting to around the 10 to the 30th decimal place. Well, quantum mechanically, I could fluctuate into a cloud of dust. That would be a very bad end to my experiment. Okay, so that gives a systematic degree of error. Or one of the more mild things that can happen, there could be a little quantum fluctuation in my brain, and instead of writing down 7 in the 10 to the 30th decimal place, I write down 2 instead. Okay? Any finite apparatus has an irreducible degree of uncertainty associated with it. It can only remove by making the apparatus infinitely large, having infinitely many components. However, gravity doesn't like this. Gravity doesn't like this division of the world into an infinite part that's doing the observing and a finite part that's being looked at, because everything gravitates. And if you try to do measurements in a fixed room, and you try to make the apparatus bigger and bigger, it gets heavier and heavier. And what happens eventually, it gets so heavy that it collapses the entire room into a black hole. And then you can't do the experiment over and over again because you get sucked into the singularity of the black hole and you die. Okay, so there is simply no way of talking about precise measurements in the interior in any finite region of space and time. It's a very kind of striking thing that there simply are no meaningful, completely well-defined observables that we can talk about in finite regions of space and time. This is due to very basic facts about what quantum mechanics lets us talk about and the universality of gravity. Therefore, the only kind of observables we are allowed to talk about involve strange experiments where we push the apparatuses off to infinity. And we let the apparatuses shoot some particles into the middle of the space-time, they bang into each other, they come back out to infinity. Those are the kinds of observations that we can, in principle, give perfectly well-defined meanings to. And this is a very highfalutin, very abstract seeming thing. It's very fortunate that these are exactly the experiments that our friends, experimental particle physicists, do for a living. That's how the main kind of experiments we do in particle physics are exactly this. I've talked about the Large Hadron Collider many times. It's 27 kilometers around. It's colliding protons that are 10 to the minus 14 centimeters big. And 10 to the minus 14 centimeters is 27 kilometers. It's pretty close to infinity compared to 10 to the minus 14 centimeters. So more or less, particles are coming in from infinity and going back out to infinity. Okay? So these are the kinds of observables that we're allowed to talk about. They're both important. Important conceptually, in that they're what quantum mechanics and gravity allow us to talk about, and they're important practically because they're exactly the things that we measure in real experiments. Now, a lot has happened over the last 20 years. These next two slides could be the subject of several colloquia, so I'm just flashing them up here just to give you some idea of the historical context. Something that the string theorists realized in the late 1990s is that following this kind of ideology, that the only kind of observables you're allowed to talk about live at infinity, could be applied very fruitfully in a class of spacetimes that are not our spacetime, but which have many qualitative features in common. And where you can make a lot of progress, where you can put the universe in a box. Physicists love to put things in boxes, and the closest you can have to put a gravitational system in a box is known as anti-de Sitter space. I won't say anything about it, but the geometry sort of looks like the inside of a tin can, but it's a sort of a warped geometry on the inside, and the warping has the feature that the distance from a point in the center to the walls of the tin can is infinite, but it's like a box, and that light bounces off the walls in finite time. Okay? So if in this system you ask, what are you allowed to talk about from the same fancy stuff that we talked about, the answer is you ping the walls of the box, waves come crashing in, come from infinity, they come crashing in to each other on the inside, they come back out. And those are the kind of observations that you can make. And in this setting, string theorists realize that those experiments start and end at infinity. And there's actually a theory that only lives on the walls at infinity that actually calculates those things. And in a very precise sense, the interior, the space and everything else, and gravity and even strings in the interior emerge out of the very strong interactions of completely ordinary particle physics on the boundary. So this is our first sort of gateway drug into the idea that space-time could be emergent. Here we see that space can emerge. Space and strings and gravity can emerge out of a quantum mechanical system with incredibly strong interactions between the particles, so strongly interacting that you don't want to keep track of what the individual particles are doing anymore, but the collective excitations of all the particles in concert, like a hologram, encode the existence of an extra direction of space and gravity and even strings and so on. Okay? So that's the theorist's playground. And the opposite extreme is reality, okay, unfortunately, because our universe it differs from this universe in a box in a very important way. The deepest, most existential facts about our universe have to do with cosmology. The fact that the universe was born at some time. So this is not some infinitely, forever living, eternal box. The box was born. It's not a box. The universe was born at some time. And in fact, more startlingly, over 20 years ago, our cosmologist friends taught us that the universe is accelerating. The expansion is accelerating. That has a very dramatic consequence, that when we look out, what we see in the sky today is everything we're ever going to see in the universe. We're never going to see any more, because the light from very distant stars, or whatever's out there, will never make it to us. The universe is doubling in size at a uniform rate, and the extra space that's being created makes it impossible for us to see anything which is out there. That means that there's a fundamental finiteness that's thrust upon us simply from the fact that we live in this accelerating universe. And that finiteness is enormous. The number of degrees of freedom in principle we can have access to in our observable universe is 10 to the power of 10 to the 120 sort of degrees of freedom. That's an enormous, enormous, but finite number. And that finiteness, again, is in tension with quantum mechanics. Quantum mechanics doesn't like finiteness. Quantum mechanics needs some things to be infinite to do the experiment infinitely often and to do the experiment with infinitely large apparatuses. Those infinities are taken away from us. We don't have them, and so we simply don't know how to make sense of any kind of precise notions of physics in this accelerating universe. So in order to understand these deepest questions about the origin and fate of our universe, we need to understand not just the emergence of space, but of space and time. And it's very likely, at least I think this is a more controversial statement, but it's very likely that this is going to need some extension of our ideas of quantum mechanics. I'm not saying some crackpot thing like quantum mechanics is modified in any way. I believe in every situation where quantum mechanics gives well-defined answers, it gives the correct answer. But these are situations where quantum mechanics cries uncle, and it's incapable of giving answers to certain kinds of questions that involve applying quantum mechanics to the entire universe. All right, so I've talked about very highfalutin things, airy-fairy things for the past 20 minutes. But so far, this is just trying to motivate that we are in a situation where there are reasons to expect our notions of space-time and quantum mechanics are approximate and have to be replaced with something else. So is there some deeper structure that underlies space-time and quantum mechanics? I think if so, it must involve new physical ideas and new mathematical ideas. It's very, very unlikely that it won't have a large degree of novelty associated with it. And I want to take some inspiration from similar periods. I think the only comparable period in the history of physics that I can think of is the transition we had to make from classical to quantum mechanics that was similarly revolutionary. And the kind of only solace that I can take is the following, that I like to imagine the thought experiment where you go back, the ghost of theorist's future goes back and visits a classical physicist in the year 1850 and says, I have news from the year 1930, determinism is gone. And they vanish into the night, as ghosts of theorist's future are wont to do. And what would this poor classical physicist who got this news do with this information? Not clear. They can't sleep. Clearly, they're not going to guess quantum mechanics in one go. They could do idiotic things like add stochastic terms, random terms to the right-hand side of Newton's laws, F equals ma plus some random crap. And that's obviously going to be wrong. But they could try something else. They could say, how could it possibly be this notion of determinism is gone, right? It's hardwired into the Newtonian clockwork universe, which is what I think physics is about. How can it be this thing that I think is built into the definition of what physics is about is gone in like less than 100 years? Well, whatever it means that if it's really gone, there has to be some echo of that, some dramatic echo of that now in the physics that I have under my feet at the moment. In other words, if determinism really isn't there, the determinism in Newton's laws must somehow be a little bit of a mirage. There must be some other way of thinking about Newton's laws where the notion of determinism is not sort of the star of the show, but kind of comes out as a consequence. The second way of talking about Newton's laws should be the way that kind of continuously deforms to the correct theory that I don't know what it is yet. Okay? Is there such a way of talking about classical physics? If you're a high school student or early in college, you're very excited to discover the principle of least action, Lagrangians, okay? This is an amazing thing. It's a way of thinking about classical physics that definitely doesn't look like the particle goes next because the force tells it what to do. Instead, it looks like the particle sniffs out every way it can go from A to B and chooses a path that minimizes the action. So it's sort of thinking about where it's going. Sure doesn't feel deterministic. And in fact, the determinism is sort of an output. It comes out at the end of the calculation that this is equivalent to Newton's laws. But the philosophy is radically different. And this happens to us occasionally in the history of development of physics, that there are many seemingly radically different philosophical starting points for describing exactly the same fundamental phenomenon at the end. And it's important to learn what all those different ways of thinking about things are, because some of them will be better suited to the next level of description than others. Okay? In this case, the principle of least action is the way that naturally generalizes the quantum mechanics, because as Richard Feynman and friends taught us 65 years ago, that's how we think about motion in quantum mechanics. A particle really does take every possible path from A to B, but we're supposed to do something. We're supposed to average a phase in an exponential e to the I, the classical action of the path. And in the limit, where the actions are large compared to Planck's constant, this reduces to a classical physics. So that's what happened in the classical to quantum transition, and where we are today is that we need to do something similar with space-time and quantum mechanics. Okay? So at least this is my guiding principle, and there are many other strategies, many other points of view about this. But this is a point of view that I like because it's not speculative. We're looking for some profound clue in the structure of established physics of the world we see around us. Okay? But we want to learn how to conceptualize that physics from a new point of view where these seemingly fundamental notions of space-time and quantum mechanics are not primary, but somehow end up coming out from more primitive ideas. So this last 25 minutes now has been totally abstract, and we're going to spend the rest of the talk making it very concrete. Okay, so that's, I think there's a few examples now we've seen over the past 10, 11, 12 years that show very concretely how this can happen. Okay, and it's not totally general. We can't do it for random theories, every possible thing. But there is something out there, and we're getting closer and closer to be able to describe more and more general things which are more and more directly connected to what we see in the real world. And it's a path you can take where your nose is to the grindstone, right? And you can check whether you're right or wrong all the time. You're not speculating about something new. You're trying to understand what's under our feet from a different point of view. All right, so now let me give you, but before going on to the concrete examples, let me tell you what most people giving a talk like this would not spend the first 25 minutes the way I did. They would immediately go to this, which is in some ways much more striking right to begin with. I told you we care about scattering amplitudes amongst other things because that's what our experimental colleagues do all day long at experiments like the Large Hadron Collider. I want to emphasize this is not the only reason we care about them. This is still a rather esoteric thing, but these elementary particles are banging into each other all the time, whether you like it or not. Okay, so hundreds of thousands and billions of times a second in the atmosphere, two protons are hitting each other with energies that are comparable to things that are happening at the LHC. These are natural processes. Everything, almost everything we see in the world around us is concatenations over and over and over again of elementary particles banging into each other. It's the most basic process in our nature. Okay, so that's why we really care about them. But in particular, to understand them in super detail, you need to understand them in order to interpret experiments at the Large Hadron Collider. And so the LHC collides protons. Protons are made out of quarks that are held inside the proton with gluons, all very imaginatively named. And what we're supposed to do, what we really care about, are sort of head-on collisions between the elementary particles that are inside the protons. Okay, so you have this messy bag around 10 to the minus 14 centimeters big of quarks and gluons here, another messy bag here, and we're interested in the head-on collisions between those particles. And we have to be able to calculate, again, there's billions of collisions a second. So we really need to understand what comes out of these collisions in order to be able to interpret the data and maybe look for hints of something beyond the standard model. Anyway, there's by now what made Richard Feynman famous in the late 1940s is that we know how to think about this physics. So in this picture, these are the little wiggly lines are supposed to represent sort of two gluons, one from one proton, one from the other proton. They bang into each other, and we're supposed to draw these pictures. Feynman's instructed us to draw these pictures that correspond to every possible way that gluons could come in and interact with each other and go out. So this would be a process of two gluons coming in and four gluons coming out. And you're just supposed to draw all the ways it could possibly happen. And there's some specific mathematical expression associated with each one of these pictures, each one of these Feynman diagrams. And the end result of all of this gives us something called the scattering amplitude. And we have to take the square, or the magnitude squared of this amplitude to give us the probability for this process actually happening. Okay, so that's where the quantum mechanics comes in. So we got two things going on. These pictures, that's why Feynman is justifiably famous. The pictures make the locality of the interactions in space and time manifest. These are space-time processes. But we make the adherence to quantum mechanics manifest by this picture that we sum over every possible history in which the process could have happened. That's the quantum mechanics part. That's why we've got to add them all up. Now, this looks complicated. There's no reason a priori the answer should not be complicated. Not every question has a simple answer. Part of the chauvinism of fundamental physics is to declare as interesting only those questions that have simple answers. And so this looks a priori not like an interesting question. It looks like an engineering problem and not a fundamental physics problem. Now, this is not a pejorative, okay? That just not interesting to a fundamental physicist. But and this is what you get. You get like 100 pages of algebra. It looks complicated, feels complicated, looks complicated, seems like it is complicated. But physics also is a wonderful way of rewarding morally good behavior. Sadly, not like society. And the physicists who actually had to do this calculation, because the experimentalists needed the answer, discovered a little over 30 years ago the following extraordinary fact, that these hundreds of pages of algebra, in some happy cases, I won't tell you what all those symbols mean, collapse to a single term. Okay, so there's just massive cancellations going on in the middle of this formula, so that these hundreds of pages collapse to a single term. Back then, in the late 1980s, when this was first discovered, this was not universally recognized as the tip of a gigantic iceberg. Today, we know it's the tip of a gigantic iceberg. And it's the iceberg that we're trying to understand and study from many different points of view. And again, the rest of the talk, I'll give you one very particular point of view about what the iceberg might be about. Okay, but what we now know is that it certainly is clear that Feynman's way of doing this physics, that remember, has a purpose in life, to make the rules of space-time and quantum mechanics completely manifest. This is doing that. That's correct. No one is doubting it's correct. Perfect, beautiful, great. But somehow it's hiding something else. It's hiding the fact that the hundreds of pages collapse to a single term. And now, remember, from the whole highfalutin psychobabble of the first part of the talk, we have reason to say we should maybe think about some way of doing physics where space-time and quantum mechanics aren't the input, but somehow come out as the output. But now we have much more concretely. You make space-time and quantum mechanics the stars, you're rewarded with 100 pages of algebra. The answer is a single term. Okay? So there has to be some way of thinking about where this physics is coming from, where the fact that it's a single term is obvious. And very likely from that point of view, the space-time and the quantum mechanics are not going to be the stars of the show. But somehow, if we understand this other point of view, we're going to see where this, we might start getting an idea of the kind of ideas, the mathematical and physical ideas, and the kind of new grammar, the new language we have to build in order to talk about physics in a way where the notions of space-time and quantum mechanics are derivative and not primary. Okay, that's the goal. But as I hope you're seeing, it's beginning to become a little more concrete. Now we're trying to understand where these formulas come from. Now, over the past decade, we've been seeing the emergence of new mathematical structures in many interesting areas, areas that have not traditionally interacted with physics a lot. In combinatorics, number theory, algebraic geometry of a very particular sort, that in quite concrete examples can be seen to give rise to the rules of space-time and quantum mechanics, or along the lines of what I was telling you. And in the rest of the talk, I want to give you some flavor of what this actually looks like. So we're going to stop doing blah blah in a bit and actually get down to brass tacks and show you some examples. One of the things that I love about this subject is that the basic ideas can be explained to high school students. And in fact, the most recent ideas can be explained to junior high school students. I used to be proud that the things I was working on could be explained to high school students because they needed to know what determinants were. And what we'll talk about later today, you won't even need to know what determinants are. You just need to know what vectors are and how to add them, which I suspect in the UK you learn in junior high school, you know, sometime early in college in the US. But anyway, all right. But just to emphasize what it is that we're after, I told you early on that the string theorists have been studying and continue to study, and it's a spectacular subject, how space can emerge from the rules of quantum mechanics. Here we're trying to do something that's more speculative, but somewhat more adventurous. We're trying to understand some other set of principles. We don't know what they are yet, but where we'll see the rules of quantum mechanics and space-time emerge together. And as we'll see, they emerge together joined inexorably. So it's not like there's a quantum part and there's a space-time part. In at least the pictures that I'll be talking to you about, they sort of come together as a package. Okay? And we'll see in concrete examples how this happens. So let me say the final big picture thing that we're doing, and then we'll get down to it. So we're talking about these elementary particle scattering processes, the particles coming in from infinity and going out to infinity. Again, the experimentalists, we'll talk about this imaginary experimentalist a bunch, but the experimentalist that's sitting out here at infinity, they just throw particles in, they close their eyes, they come back after lunch, a late lunch in Geneva, and the particles come out, and that's it. That's what they see, right? They don't know that the protons were going in and there were these gluons inside the proton. They're not writing in the proton, right? They just do this experiment in the morning. They come back in the evening. So who is it that's telling them that there are these gluons in the proton and they bang into each other? This happens, that happens. You add them all up. It's the theorists telling them that. It's the theorists that are telling a story for what happens inside this blob while they're relaxing, okay? They're not relaxing all the time, but anyway, they also work. just not as hard as we do. I'm kidding. Now, so it's a theorist who say there's a story for what happened on the inside, which involves local evolution in space-time and also evolution in the Hilbert space of quantum mechanics. So those are sort of two auxiliary constructs that this experimentalist doesn't know about. Okay, they don't know about all this stuff, but it's a theorist who says, no, there's this wave function evolving in Hilbert space. There are these local interactions in space-time, and that's what's going on. And so what we'd like to do is find a different question to which the amplitudes are the answer. The conventional question to which the amplitudes are the answer is idiot. It's local unitary evolution in space-time. And what we're trying to do is find a different question that does not include this auxiliary space, that is not part of the data that the experimentalist measures. Okay, we don't want to introduce any of these auxiliary things. We want to ask a question directly, if you like, in the kinematic space, in the space that labels the scattering process. We want to ask a question there that somehow has all the richness and complexity, a new kind of question that has the richness and complexity that allows us to get the amplitudes out as the answer. And if we can do this, hopefully, we can see how this something else gives rise to the properties of amplitudes that we ordinarily ascribe to local evolution in space-time and the unitary evolution of quantum mechanics. All right, so now let's start getting into it. One of the key ideas here is the notion of on-shell versus off-shell. And so if you know anything about particle physics or Feynman diagrams, even at a lay point of view, you might have heard that when we draw these pictures like Feynman does, that we have these off-shell particles in the middle. They're virtual particles. We even use this language of virtual particle. What is this thing that are virtual particles? Well, they're not real particles. What is a real particle? Well, we have a particle, it has some energy, it has some momentum. We can group them into a four momentum, but they're not independent of each other. They satisfy that the E squared minus P squared is equal to the mass squared of the particle. So we call that the on-mass shell condition, because this sort of defines a hyperboloid, where E squared equals P squared plus M squared in P space. Okay? But when we draw these pictures, you see this guy on the inside, the guys on the outside satisfy P squared equals M squared, but this momentum on the inside is, let's say, the sum or the difference of those two momenta there, and that will not satisfy that it's on shell. That's a good thing, because in our ordinary rules that we learned from Feynman, we actually have to associate with this guy a factor that's 1 over P squared minus M squared. Precisely how off the mass shell it is part of the contribution this makes to the scattering amplitude. Okay, so this is ubiquitous in our picture for what the amplitudes are. And so the most basic physical idea is to eliminate this notion of virtual particle. We don't want to talk about virtual particles, okay? Because the presence of virtual particles exactly signifies particles that don't travel infinite distances from the past infinity to future infinity. They propagate over finite regions in space and time. And so that their presence tells you we're talking about the interior of space-time, exactly what we don't want to have. So we want to get rid of the notion of virtual particle, but if we get rid of the notion of virtual particle, how can we even, is there some property of the amplitude that kind of, that's a stand-in for the presence of those virtual particles from the conventional point of view that we can use to sort of diagnose whether they're there or not without explicitly having to talk about them, and there happily is. So let's say I have two particles in and two particles out. Here is a process where, in the conventional language, there would be a virtual particle in the middle. If I tune the momenta of the particles on the outside, I can tune it so that this virtual particle in the middle becomes real. Now, what happens when we do that? That's exactly like resonance, right? That's exactly like ordinary resonance. And the amplitude literally blows up. At least in some approximation, the amplitude becomes very large. In some zeroth approximation, it literally blows up. And why is it blowing up? Because I'm actually producing a real particle. Okay, so that's a way that the experimentalists could know there's something going on. By twiddling the dials of the momentum on the outside, they can make the amplitude blow up somewhere. That's exciting. So the fact that it blows up only when the P1 plus P2 squared equals M squared, that's a sign of locality in space-time. If it was a random function, it could have been 1 over, I don't know, let's call P's, things like P1 plus P2. It has to look like 1 over P squared minus M squared. it could have been 1 over p squared q squared minus r squared t squared, much more complicated function. And those things, if they were there, would not correspond to producing a virtual particle that travels over a long distance. Okay? So the kind of singularities that the amplitude has, the kind of ways that it blows up, is a diagnostic for locality. It has to have these very simple kind of singularities that correspond to just poles when p1 plus p2 squared goes to m squared. So that's locality. And right away, quantum mechanics also tells you, the rules of quantum mechanics also show up in exactly the same spot. Because now quantum mechanics tells you that this amplitude, as it's blowing up, has to have a consistent interpretation that you actually produce this intermediate particle with some amplitude, and then it just propagates at very long distances and it decays out on the other side. So the amplitude in the neighborhood of when p1 plus p2 squared is close to m squared actually has to factorize into this sort of pole part, but when it multiplies has got to be interpreted as the product of 2 lower point amplitudes. So we call that, in these at least very simple case, for obvious reasons, factorization. Okay, so that's locality, is where the singularities are, and the unitarity of quantum mechanics, the rules of quantum mechanics at this level of approximation are just reflected in this very sharp way in the statement of factorization. So here I'm just saying it again. Here the rules of space-time and quantum mechanics tell us that locality is that the only poles are when a sum of the external momenta goes on shell, and unitarity tells us there's factorization on those poles. All right, so now we're starting to get somewhere, because now we have a more concrete strategy now. So when I say we want to find a question that doesn't involve space-time and Hilbert space, a question directly living in the space of the momenta of the actual particles that we see, what we want to do is find a different question that's directly in the kinematical space to which these functions are the answer, without referring to space-time and quantum mechanics, but which nonetheless gives the correct poles and the correct factorization properties. Okay, so that's it's starting to become a more concrete version of our grand challenge. And coming back to what I mentioned before, the emerging picture over the past 10 years is that in this kinematic space, and I stress this kinematic space seems like a very boring and arid space. If I have n particles, it's, to begin with, it's just a space of n 4 vectors that satisfy p squared equals m squared, okay? Just a space of n 4 vectors. What the heck can we do in the space of n 4 vectors? That's our canvas, that's our playground. In the space of n 4 vectors, we have to learn to ask a new kind of question whose answer is going to give us amplitudes, okay? So that's our goal, but now they have to give us amplitudes with these particular properties, okay? Poles in the right spot and factorization. And what we've been seeing is there's not much to do in this space, but there's just enough structure to proceed. And there's a picture, the emerging picture is that in this kinematic space, there are certain combinatorial ideas that are associated with some geometric ideas. So there's natural ways of associating geometric shapes. They're not like they're not like fancy looking geometric shapes. It's not like what you see in, you know, the elegant universe, fancy Calabi-Yau manifold. They're much more austere, basic looking geometric shapes. They're fundamentally geometrizing certain combinatorial notions. And these in turn are associated with some analytic ideas. Okay, so some, and that's ultimately where the connection to amplitudes comes from. Some of the words associated with these stories are for the scattering of gluons, literally in the leading order approximation, the process that I was talking about. This is associated with an interesting set of geometric object known as amplituhedra. In the rest of this talk, I'll talk about a much more basic class of, a basic and simple class of objects of this sort that are associated with the words isosahedra, things that I'll call surfacehedra a little more generally towards the end of this talk. There are versions of these, analogs of these ideas that are beginning to be seen in the context of cosmology now, not just for scattering amplitudes, but for the ultimate cosmological questions that I motivated a little while ago. These are very baby examples, but they're still steps in the right direction. And just to reiterate what I said before, what I find exciting about this subject is that it describes real-world physics. in some reasonable approximation. These are not toy models, very, very far from reality. There are things that recognizably have things to do with stuff that happens in nature all the time. That's very, very important to me personally as a physicist. And it exposes some hidden symmetries and new mathematical structures and sort of pure magic in physics right under our noses. Okay? Let's begin with the first invitation to why there's anything like this going on. So I'm going to talk about the very, very simplest possible theory now in a little bit more detail. These are now theories not even as things as complicated as gluons that have spin. These are just elementary particles with no spin at all. Things maybe perhaps a little bit like the Higgs boson. And we're going to imagine that that I'm just drawing all these simplest Feynman diagrams. And the particles are ordered. Okay, so they come in some order, 1, 2, 3, 4. We'll talk about that ordering again a little later. But you're just supposed to draw all the stick figures you can with these basic cubic 3-point interactions, just this basic little 3-pronged blob. You put them together, but all the diagrams should be drawn on a plane. They can't cross each other. Okay, so none of the lines in the diagram can cross. So that's what you get for 2 particles in, 2 out. So this 4-particle amplitude just be 2 diagrams. For just skipping to 6 particles, there would be 14 diagrams. These are 2 of them. Okay. All right. And just to make a quick comment, like in this case, what are the poles that we see? In this intermediate line, it would be P1 plus P2 squared minus m squared. This one would be P2 plus P3 squared. What about this one? That would be P1 plus P2 squared. That one would be P1 plus P2 plus P3 squared, and so on. Okay? This one would be P3 plus P4 squared, P3 plus P4 plus P5 squared for that one, and so on. Okay? So, sorry, this is just P3 plus P4 squared, P5 plus P6 squared, and so on. So the only poles you ever see involve consecutive momenta. Okay? Remember, there's an ordering for the particles, so they involve consecutive chains of momenta. There's actually a very convenient way to keep track of what all these variables are. Let's just take a moment to think about them, because this is going to be our playground for the next 20 minutes. Okay? This is going to be the space where we live, where we have to find a way to ask a question. Okay? Our playground is going to be, in order to think about these variables, the conservation of energy and momentum tells us that these momenta all add up to 0. So I take P1 plus P2 plus blah, blah, blah. They all add up to 0. That means if I draw them on a piece of paper or on a d-dimensional piece of paper in d dimensions, they would form a closed polygon. Okay? The sum of all the momenta add up to 0 if I just draw one vector after the other. So it's very natural to look at what the distance is between 2 points here. So the distance between this point 1 and 4 would just be P1 plus P2 plus P3 squared. Those are exactly the variables that we see in the propagators. That's very convenient. Okay? So and in fact, you can show very easily that all the possible dot products that you can make out of these d vectors, the number of independent such dot products is exactly the same as the number of these chords of the polygon. So these are not only the variables that we see in the amplitude, they're also a basis for all the kinematic variables that we could have for this simple problem. Okay, so these are our variables. I'm going to call this combination xij, that's labeled by the curve. And so that's our kinematic space. That's what the actual amplitudes depend on. They just depend on these xijs. So now I want to go back to that imaginary experimentalist who has their finger on the dials of the momenta. Really, it's the finger of the dials of these xijs. They're moving these xijs around. What do they see? What are they excited about? Well, they would notice, I'm only going to tell you what a lazy and smart experimentalist sees. A hardworking experimentalist that secretly wants to be a theorist would actually notice what we've talked about already. They would notice that as you dial these x's, sometimes the amplitude blows up. So they'd be very excited that it blows up, and they would notice that on the place where it blows up, it factorizes into the product of simpler amplitudes. Okay, so that's what the closet theorist experimentalists would notice. But there's another experimentalist who hates theorists. Okay, this is most good experimentalists. Okay, and they don't care about doing any detailed measurements. They see the amplitudes blow up. They're excited about making it blow up more. Okay, so they're like a little kid. They make the amplitude blow up, And they say, I haven't made it blow up. Can I tune some of the rest of the variables to make it blow up twice, 3 times, 4 times? Okay? So for instance, at 4 points, they would discover that, yes, that's great. I can make it blow up when P1 plus P2 squared goes to M squared. But once I do that, I can't make it blow up any more than that. In particular, it doesn't blow up when P2 plus P3 squared goes to M squared. So it can blow up when one of them goes to M squared or the other one, but not both. Okay? And why is that? Well, secretly, because we have this space-time picture, it's because we can't have those 2 pictures happening at the same time. We can either have one picture that it went this way or the other picture where it goes that way, but not something where both of them happen at the same time. That's the physics of space-time locality. Okay, let's go to 5 points. Now this is a little more interesting. There's a pattern to how the blowups can happen. For instance, it can blow up when P1 plus P2 squared goes to M squared. But if you do that, you can make it blow up more by making P1 plus P2 plus P3 squared go to M squared as well. You can make it blow up twice. You can't make it blow up 3 times, though, or any further. Now, why is that? Again, secretly, we know what's going on behind the scenes. It's because we have these pictures now with 2 sets of propagators in the middle, but not 3. Okay? And I can have P1 plus P2 squared and P1 plus P2 plus P3 squared. But I can't have P1 plus P2 squared and P2 plus P3 plus P4 squared. Again, because there isn't a space-time picture where those 2 things happen at the same time. So there's an interesting pattern in what sets of double poles you're allowed to get. And then when you go to 6-point scattering, there's an interesting pattern of triple poles can come together. Without doing any detailed measurements of what's happening, factorization, nothing, right? You're just looking at a pattern of how the poles come together. Now the fascinating thing, and let me just say this in the language of that polygon that we are drawing. In this language, it just says there are certain patterns of poles that are forbidden. If I remember, every propagator here is associated with some chord on this diagram, and if I have 2 crossing chords, that never happens. Okay? But if the chords don't cross, those poles can come together. Okay? So sometimes I'll slip in the language of calling these chords compatible or incompatible. If they're incompatible, if they cross, that means that there's no space-time process that has those propagators at the same time. All right, so that's kind of interesting that crossing chords are forbidden, non-crossing chords are allowed, and these are the examples that we talked about before. But now this experimentalist, just to say again, the pattern of who is allowed is encoding locality, and what happens in the neighborhood as one of the xij's goes to 0. What happens as an x goes to 0? Well, what happens is the amplitude factorizes. What does it factorize? Exactly into the amplitude that you'd associate with this left polygon and the right polygon if you just literally cut along the lines of that xij. All right, so again, we're getting a little more concrete all the time. Now, what's our playground? The space of all chords on this polygon. What are we looking for? Something in the space of chords on the polygon that has the property that crossing chords are not allowed. And that non-crossing chord, if you give me one chord, there's some natural reason it breaks up into the product of 2 similar objects of the same sort. Okay? And so we want the question that's going to have that as an answer. Okay? Now, going back to our hero experimentalists, they want to report the pattern of how the poles come together at their experimental meeting. And they actually notice that the pattern of how the poles come together actually has a shape. It can be captured by a shape. And so let's start in this 5-point example. It's just completely coincidental that it looks like a pentagon. I'll show you something more amusing in a second. Completely coincidental that it looks like a pentagon. But anyway, what is this picture? You see, one of the edges of this pentagon is supposed to correspond to the presence of a pole that corresponds to 1 chord. This is another chord. This is another chord. Okay, so I've decorated all of the edges with a single chord. But notice the cool thing is that vertex is both of these chords that are compatible from the 2 edges that surround it. All right? So it says already in this case, it looks really easy, but it's not 100% trivial, that it's possible to decorate this pentagon in such a way that the edges are just single triangulation, partial triangulation of the polygon with a single chord, and the vertices are a complete triangulation with 2 chords. Okay? You can think of the interior of this shape as no triangulation at all, no chords at all, and the first facets, in these cases edges, are just 1 chord, the vertices are 2 chords, and so on. So what would I have for the case of 4-particle scattering? Even more trivial, just an interval. The inside is nothing, one end is one of the channels that look like that. The other end is the other channel that looks like that. Okay? All right, now what does it look like at 6 points is already a lot more interesting. The experimentalists would have to have a lot of imagination to do this. But if they worked hard enough, and or if their name was the wonderful mathematician Jim Stashev sometime in the mid-1960s, they would recognize that you can actually decorate all of the triangulations of this hexagon, of the sixgon, with facets of the following beautiful three-dimensional shape. Okay, so this shape is called the isosahedron. And the general object of this sort for an n dimension is called the n-dimensional isosahedron. So this would be the three-dimensional isosahedron. It's associated with 6 particle scattering. Okay, so the number of poles is n minus 3 when you have n particle scattering in this approximation. But what's remarkable about this picture is I've decorated the vertices with triangulations of a hexagon. Okay, so there are 14 triangulations of a hexagon. And I haven't decorated the whole picture because it would look busy, but there are 9 facets that correspond to single chords, and there are 21 edges that correspond to 2 sets of chords, and they are all compatible with each other. Okay, so this is a picture where the facets of various dimensionality simply record partial triangulations of the hexagon. Right? So this is the pattern of how the poles come together that this experimentalist would notice, okay, if their name was Jim Stashev. In fact, Jim Stashev did not realize that I've drawn this picture so it looks like it has flat sides. Right? So things that are just have flat sides are called polytopes. They're cut out. One way of talking about them is that they're cut out by linear equations. Something bigger than 0, some hyperplane bigger than 0, another hyperplane bigger than 0. So things that are cut out by these linear equations are called polytopes. Stashev didn't realize it was a polytope. It wasn't until the 1980s that mathematicians realized these were actually polytopes. Okay, but this is an interesting fact about how the poles come together. Very basic fact that encodes something about locality in space-time and, well, I haven't told you how it encodes those things. Yeah, this is just some basic fact that's not in all the textbooks. But this picture, in fact, knows what we knew before as well. Okay? It knows about both locality and unitarity. So the way it knows about locality is obvious because all the facets just correspond to a single chord and not some more complicated thing. All the facets just correspond to a single chord. But it knows about unitarity in the following remarkable way. If you look at this picture, you'll notice it has 6 facets that look like pentagons and 3 facets that look like squares. Okay? And in fact, these facets look exactly like products of lower isosahedra, okay, in just the way that you would associate the picture of factorization. For instance, this pentagon here is the picture you'd associate with a 5-point amplitude cross a 3-point amplitude. I didn't tell you what a 3-point amplitude was because it doesn't have any poles at all. So it would be a point in this picture. And indeed, a 5-point times a 3-point is just a pentagon times a point looks like a pentagon. So those are all the pentagons. What about the 3 squares? Well, there's exactly 3 of these ways of factorizing with 3 particles on one side and 3 on the other. And remember, each one of these 4-point guys was an interval. So what is an interval cross an interval? It's a square. Okay? So we see that this shape knows about factorization as well, because it has this wonderful property that when you go on the facets aren't some random crappy things. They're products of lower objects of the same sort in this class of things that we're seeing. All right, so this is now a clue. Okay, so you're this experimentalist, you saw this clue, and now you want to know where is this coming from, right? We want to know what kind of question. Now we're sharpening even further. Now we want to ask what kind of question in this kinematic space can we ask whose answer somehow brings to life this isosahedron. Where the hell does the isosahedron come from? Okay, what would force you to discover it? What natural question in kinematic space would allow you to discover this isosahedron? Whatever it is, this is a qualitative clue to the theory in kinematic space that we're seeking. Now, if I was giving this talk 2 years ago, I would give you a very, what I like to call artisanal talk, full of sort of clues and very simple pictures and conjectures for what was going on. That's related to the fact that back in 2017 with some friends, we discovered by accident a very particular realization of this icosahedron. So the kind of combinatorics of this picture, how the facets come together, is exactly the same as that general one, but you see it as a very, very special shape. The sides are parallel in some very specific ways. And so this was even more specific. We wanted to know where this particular icosahedron came from, because it clearly had some sort of very canonical connection to the physics. But as I said, what we're doing was quite artisanal. We sort of guessed it, and then we found all sorts of reverse engineering motivations why the guess had to be right. But you know, what you always know, as I said, one of the nice things about this business is that you know when you're on the right track when you produce new formulas. It's very easy to take known things and push things around and derive in different ways known facts. But in this business, you have to derive new facts. And you know you're making progress when you can do new things, write down formulas that have not been written down before. Okay? So we were trying to generalize from this very simplest picture for these tree-level processes to more complicated pictures with loop-level processes. And doing that is really what has occupied my friends and I over the course of the pandemic. And we believe that we now do have the sort of conceptual ideas that underlie what we've been seeing in this more, as I say, artisanal way over the past couple of years. So if I have maybe 10 minutes, 10 or 15 minutes, maybe I'll tell you a little bit about what some of these conceptual ideas are. And I really won't have time to even tell you about both parts of this title. But as we'll see, there's some very, very basic facts in kinematic space that bring these geometries to life. And quite remarkably, at least to us, these very basic facts also give us a very, very tight connection between particles and strings. Okay, so there's a way of sort of discovering the generalization from particles to strings. The particles already know about the strings. That in this way of thinking about the particles, the most basic object is essentially stringy already, and it's a very small step to make it officially stringy from this point of view. All right. For this last part of the talk, this work over the course of the pandemic has been done. Again, these are a circle of ideas that go back a decade, but this particular set of ideas is being developed by the mathematicians Hugh Thomas and Pierre-Guy Plamondon, and two wonderful young theoretical physicists, Giulio Salvatore and Hadley Frost. All right, so let me now be much more specific about the theory that we're talking about. We're talking about a theory of colored scalars. Okay, so this is just like a theory of gluons, where the gluon is a color and an anticolor, except these are just the spin zero particles that have a color and an anticolor. So, and we have this basic cubic interaction for them. Of course, the singularities, the denominators of this theory are the same as the denominators of any old theory for colored particles. So, but obviously, gluons, other kind of interaction you could have would have more interesting numerators, but this is sort of universal, capturing some universal aspect of the denominators, of the singularities of the amplitudes. And as been understood going back to Gerard de Toof from the 1970s, simply having colored particles, if you draw the diagrams involving the colors and the anti-colors, we get these, what are sometimes called double line notation diagrams, or fat graphs, or ribbon graphs. And we already get a picture associated with surfaces. So a surface comes to life here simply from the fact that I have colors and anticolors, nowhere else. Okay? And in fact, again, this is very ancient stuff that's been understood for decades by mathematicians, even decades before physicists talked about them, is that these diagrams really can be thought of as defining a surface. Not just that you draw them on some surface, but they literally define a surface. You can think of the diagram as directly giving you a triangulation of a surface. So if I take the surface, which is a disk with 5 points on the outside, here's a triangulation of it. We're drawing similar pictures before. I was just making them look like pentagons before, but it's exactly the same picture. Well, if I just put a dot in the middle of all the faces and just draw the dual of the diagram, I get exactly the Feynman graph, and I just turn them into fat lines. This picture literally defines this surface. And in fact, every cubic vertex in this picture can be thought of as a triangle in the triangulation. Okay, where every triangle is just specified by giving its 3 edges. So that's what a cubic vertex is, and when you glue two cubic vertices together, you say that those two triangles overlap. Okay, so this is a totally canonical thing. That's simply to define a surface, you give a diagram. And the definition of a surface does not even require you to see anything. Imagine you were blind. Okay, you just wanted to talk about what a surface was. Or you're talking about a super complicated surface. You don't want to draw it. There are computer programs that do a million things with surfaces. They're not drawing them or looking at them. You just hand them a sequence of triangles. You say this one, that one, that one, that one, that one. And here are the edges that are in common from this triangle to that triangle to that triangle. So that simply defines a surface. So I want to emphasize this point. One diagram simply defines the surface. Then there's zillions of diagrams with the same topology, but one diagram defines the surface. All right. Now in this language, you can also talk about kinematic space. So what are the kinematic variables? Well, you draw the surface, and with every chord on the surface, you associate some kinematic variable. So we already saw this in our previous example. Here's the surface, here's a chord, x, and what's the momentum, or the momentum squared that you'd associate with that? Well, it's simply given by the homology of the surface. So you imagine that you have momenta on the outside, and this curve can be continuously deformed to that one. And so the momentum that you associate with this curve would be P1 plus P2 plus P3, because it can be continuously deformed to the other guy. So the momenta are associated with homology, and now at this level it might depend on how you go around, but since we're squaring them, it doesn't matter how you go around. Okay, so our kinematic variables are chords on the surface. The momenta are given by homology. Sometimes, for example, if you have a surface that looks like an annulus instead of a disk, there are some of these momenta that are not determined from giving the boundary guys, like this one, L. That one's not determined, so I just give it a name, L. And then all the rest of them are now determined. I'm choosing a basis for the homology of the surface. And this is what the quantum field theorists would call the loop variables. Okay? So anyway, this is a way of labeling all the variables that you ever see associated with chords on the surface. All right. Now, having said all of this, now let's return to our very basic question about space-time and quantum mechanics in this setting. We would like to know, before doing anything else, why is it that we should consider all the triangulations of a surface? Remember, one triangulation just defines the surface. Why do I care about all of them? Okay, that's why do I care about all space-time processes? What's special about space-time processes? Why do I care about triangulations of the surface? Next question, why should I add them all up together coherently, uniformly, all the same weight? Why can't I just say, I like you, I don't like you, what's wrong with leaving some of them out? Why should I take them all together? Okay, so these are at the most primitive basic level. Why do I care about all triangulations of the surface? And why should I add them all up together? What's special? Is there anything special about adding them all up together uniformly? Turns out that the answer to this question is really lying in plain sight. Really right under our noses once we think simply about how to label the curves on the surface. Unbelievably basic question. But thinking about how to label curves on the surface is going to give us at least the beginning of an answer to these questions. And this is the part that I really think I will have zero time to tell you about. But it gives us, this picture gives us new formulas for the amplitudes. To the aficionados in the audience, I would say that much of the connection between these combinatorial geometries and amplitudes over the past decade has revolved around integrands of scattering amplitudes. And these are now for actually amplitudes. Okay? So they're really formulas for actual amplitudes. They're vastly more efficient than Feynman diagrams. You can get the 20-point two-loop non-planar trace phi cubed amplitude just on the computer by pressing return. It's totally concrete expressions that you can numerically evaluate because they're meaningful. They're analytic expressions. They're not formal, but you can really calculate with them. And of course, they'll make no reference to the Feynman diagrams. And the structure exposes some hidden symmetries. Again, to the aficionados, there is an analog of the dual conformal symmetry that we're used to in the maximally supersymmetric Yang-Mills theory in these very stupid trace phi cube theories that are made obvious by this connection to the geometry that is made manifest and which is actually concretely useful. Okay? And also this picture, which is fundamentally about particles with the 2D surface just about combinatorics of Feynman diagrams, hands us the generalizations from particles to strings with no reference to a worldsheet, no reference to a worldsheet conformal field theory, vertex operators, all the stuff that we talk about in standard ways of describing string theory. It's a different way of representing string amplitudes in a more, with some more fundamentally combinatorial ideas. But I probably won't have time to describe that. But at least this is a flash for what some of the ideas are. Maybe I'll just spend a few minutes telling you about this part of the picture. There's sort of three parts to this subject. The most basic one has to do with thinking about the labels and what's known as a fan, or a tropical fan, and associated with pictures like this. This picture you haven't seen before. This picture we saw a little while ago, the pentagon associated with 5-point scattering. And this picture is related to that one by looking at the normal vectors of the sides of this shape. The normal vectors of the sides of the shape gives us this fan, but I'll tell you more primitively where this fan comes from to begin with. Anyway, so there's three parts of the subject. There's the labels and this tropical fan. There's this set of polytopes that generalize from the icosahedron. So the icosahedron is a polytope that's associated with the surface, where all the facets correspond to cutting chords on the surface. Well, we can talk about this notion for any surface. And there is a polytope associated with any surface whose facet structure reflects pinching the curves on the surface. But now there's much richer kind of pinchings that can happen for a general polytope. And in fact, these are all infinite polytopes, because for general surfaces, we have infinitely many curves. So they have a very interesting fractal structure associated with them. So these are what we call surfacehedra. And finally, there's a third thing. These ideas are all extremely closely connected to each other. But the third thing involves studying the following very simple set of nonlinear equations that, again, you could describe to a kid in junior high school. They could start trying to solve them. They would have a lot of fun trying to solve them. But they're very simple to describe. So you take any surface, and with every chord on the surface, x, you associate a variable ux. And then you write down the following set of equations. For every x, you write down the ux plus a product over all the chords y, uy, to the exponent. And the exponent simply counts the number of times the curves x and y intersect on the surface. Okay, just the intersection number of x and y on the surface. These extremely simple equations, to the aficionados, turn out to give you a global description of the compactification of Teichmuller space associated with surfaces. Okay? But the connection to the Teichmuller space and to hyperbolic geometry is merely one way of solving these equations. There's a number of ways of solving these equations. One of them connects to hyperbolic geometry in something that looks like a description of a string worldsheet. It's not the most fundamental way of solving these equations. The most fundamental way of solving them involves other ideas, more basically combinatorial ideas, and most fundamentally associated with the category of quiver representations. And these are words that I never in a million years would have thought I would have said even 3 years ago. As a dyed-in-the-wool normal theoretical physicist, I would have never thought that anything about category theory would be useful for anything ever, and I was completely wrong. Okay, 100% wrong. There's something very deep, profound, and beefy, real formulas that I certainly would have never guessed myself, but which are associated in a very basic way with counting problems associated with quiver representation theory and thinking about the category of quiver representation theory. Okay, so this has real content, although I won't have time to tell you about too much of it. But just to say, this part of the story is all about particles, and these are nonlinear. It's all about particles, and you see it's all sort of linear, or what you might call piecewise linear. You'll see what I mean by that more precisely in just a moment. This part is curvy. Okay? This part is some sort of nonlinear curvy equations, and these two things are achingly close to each other. Okay? But the piecewise linear part is all about particles, and the curvy part is about strings. Okay? And the passage from one to the other uplifts these new formulas for amplitudes that I was telling you about, from particle formulas to string formulas. All right, but anyway, let me at least tell you something concrete, not just advertising, to tell you at least where some of these things come from at the most basic level, where why we have to consider all the diagrams together, why we even care about diagrams, and why we should consider them all together, because this part you can really, this part we can do start to finish. Okay, so what we're going to do is just think about the curves on the surface responsibly. So the curves on a surface are actually words. And here are the words that they are. So let's go back to our example. Here's our 5-point example. And I want to talk about some curves on the surface. The way I was drawing them before, I would draw maybe this chord 1, 3. But it's actually going to be slightly more natural to imagine pushing the endpoints of the curve a little. So instead of 1, 3, I go a little bit to the right of 1 and a little bit to the right of 3 to this red curve. Okay, so the technical word is that this is called the lamination, this is called the chord, the blue thing is called the chord, the red thing is called the lamination. There's various motivations for this, but let me tell you the most basic motivation for it is that that's what you would do if you're drawing the fat graph. If someone said, look at the fat graph, and what are the curves on the surface? What are they? They're just roads that you can travel in this graph. I'm going to go here, I'm going to go there, right? So that's what a curve on the surface looks like. The surface is defined by one of these pictures, and then every possible curve on the surface is just some road you could walk down, okay? So how would I label what road to walk down? You're trying to tell your friend to take this road? Well, you'd tell them to do Google Maps, right? So how are we going to label the curve? We're just going to tell you what to do. So this curve, 2, 5, I say I start the road 2, 3, make a left onto the road 1, 3, make a right onto the road 1, 4, make a right onto the road 5, 1. All right? And clearly, every curve on the surface can be represented in that way. I'm going to draw pictures here where making left is going up and making right is going down. Right? So now on this surface, how many curves are there? There are 10 arcs that we could talk about. 5 times 2. There's the 5 guys that would be the laminates that would go from, instead of 1, 2, I would draw it from a little bit to the right of 1 to a little bit to the right of 2. So 1, 2, 2, 3, 3, 4. So I have those 5 guys. And I also have 1, 3, 2, 4, 3, 5, and so on. Those 5 guys. So I have 5 plus 5 equals 10 curves on the surface, 10 laminates. So far, so good? Right? And here are the words for all of them. You can do them yourself, but here are the words for all of them. For example, 1, 3, literally this one is 1, 2. You make a right to 1, 3. You go make a left onto 3, 4, and so on. All right, so giving the curves on the surface is just giving all these words. Now, an even more basic thing that you could do is to record simply which roads you hit. Don't even say whether you went left, right. You just say which roads did you hit. So here I have a natural, a basis to talk about 1, 2, 2, 3, 4, 4, 5, 5, 1, and 1, 3, and 1, 4. That's my sort of triangulation here. So it's a 7-dimensional space. Every curve is associated with a 7 vector. Right? And it's just either ones or zeros, whether on that curve you hit the road or you don't. Okay, so every one of these 10 curves is associated with a certain 7-dimensional vector. So what is a 7-dimensional vector for 1, 4? Its entries are in 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, 1, 3, 1, 4. And this would have would have entries 1 in the 1, 2, 1, 3, 1, 4, 4, 5 slot and 0 elsewhere. Okay, I just want to be super explicit. This is a totally trivial idea. Just the dimensionality is a little big, 7-dimensional vector. Okay? But the set of all curves on the surface, I just plonk them all down. I just have a ton of these 7-dimensional vectors. Okay? Nothing interesting is happening so far. I can, for example, since there are 7-dimensional vectors, I can take all of them and expand them in a basis of 7 of these 10. And there's a very natural 7 set to take, which is simply the laminates associated with 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, 1, 3, and 1, 4. Okay, those are exactly the ones that we had in our triangulation to begin with. And so that means that I can express the remaining 3 guys, 2, 4, 2, 5, and 3, 5, as a linear combination of that basis of 7, if I like. Okay, so I just did it for you. This is just what the exercise is, to write them as a linear combination. So far, nothing interesting is happening. And the first bit of magic now happens, which is that we want to do something which is analogous to going on shell in this picture. And remember, there's some distinction between the laminates that are 1, 2, 2, 3, 3, 4, 4, 5. Those correspond to curves that aren't actually dynamical variables on the surface. those are locked to be m squared by the on-shell conditions. Okay? So there's a difference between those guys and the rest of them. How can we put that difference into the picture? What we're going to do is take this configuration, the 7-dimensional configuration of vectors, and we're going to just look at them in the directions associated with the boundary guys. So we're just going to stare at the 7-dimensional picture in the direction of the 5 vectors corresponding to the boundaries. So technically, we just say we project through the boundary configurations. So now that's going to take us from a 7-dimensional picture to a 7 minus 5 equals 2-dimensional picture. Okay, because I'm projecting through 5 dimensions. And let's look at what we're left with once we do this. It's very easy to see what we're left with because I've given you the formula for everyone in terms of this basis of 7 guys. And projecting in the directions 1, 2, 2, 3, 3, 4, 4, 5, 5, 1 just means that I lop off everything in those directions because I'm projecting in them, right? So they're just get projected to 0. So what am I left with? I'm left with I'm left with vectors for the 5 variables that are not the boundary guys. Okay, so there's some vector for 1, 3 and for 1, 4. They're a part of my basis. And here's a vector for 2, 4. See, I can see what the formula is up here. It's the 1, 4 minus 1, 3. This thing has gone to 0. So in this 2-dimensional space, it's 1, 4 minus 1, 3. This guy's negative G1, 3. This is negative G1, 4. Okay. And there's a little shortcut pattern you might notice already. You didn't have to go through all this song and dance. You could actually predict ahead of time what all these linear combinations were just from the words. Okay, if you take the word and you just stare at the word, and everywhere there's a valley, you put down the corresponding variable of the plus sign, and everywhere there's a peak, you put the value of the minus sign. That exactly gives you this geometric vector. It's very easy to prove that that is the case. Okay, so given the word, there is a set of vectors associated with it that you can just read off from the word that does this sort of process of projecting through the boundary guys to just go down to the sort of actual variables that can vary, the actual dynamical variables. And now there is something slightly magical. Okay, so let's look at this set of vectors that I have. So here's 1, 3, 1, 4, 2, 4. Remember, it was minus 1, 3 plus 1, 4. 2, 5 is minus 1, 3. 3, 5 is minus 1, 4. And if I look at it, look, this has now covered the entire space. That wasn't true before. Before I had these 7 vectors, they all had positive coefficients, they're all sort of pointed in some direction. After I project, they're covering the entire space, but they're breaking it up into little pieces to cover the whole space. So who are these pieces? Well, this guy's bounded by 1, 3 and 1, 4. Well, that's one of the triangulations of the polygon. That's a Feynman diagram. This is another triangulation of the polygon. Every single piece here is actually a triangulation of the polygon. I didn't ask for this. I didn't say, I like triangulations of the polygon. I like space-time processes. I don't care about them. I just take the picture, I take the words, I go on shell, and what comes out of it is that the space is tiled by cones. And the cones correspond to all the triangulations of the polygon. Okay? So all the space-time processes come out, and they completely cover the entire space. And you can't leave any of them out without ruining the fact that they cover the entire space. So the most basic level, this is how we see the need for all possible space-time processes and taking them all into consideration at the same time. And that ends up being true for any surface. There's all sorts of novelties associated with it that I don't have time to talk about. The final thing I'll say quickly for the aficionados is that this picture where we have a sort of a fan which divides space into segments, each one of which corresponds to one diagram sort of automatically, naturally, gives us an opportunity now to do something that you might have wanted to do before, which is to give a unified way of writing the sum of all the diagrams as a single integral over generalized Schwinger parameters. And we can actually do that. This picture allows us to at least begin with take the fact that we tile the whole space with Feynman diagrams and introduce some formal set of variables that are piecewise linear on the space that have the property of turning into the Schwinger parameters we want in each cone at a time. And you can do that. You can do that for any surface if you could come up with these piecewise linear functions. And that gives you an analog of Schwinger parameterization, but now where all the diagrams are combined to single objects. So again, these are like some unified form of Schwinger parameterization, and they're associated with the generalization of the semantic polynomials that you're used to with Schwinger parameterizations for single diagrams into summing all the diagrams together at once. But the sort of magic is it possible to find in a useful way these piecewise linear functions that do what needs to be done? And you could try to do this for a totally random fan, and it's possible to do for any fan, but doing it is as complicated as enumerating all the Feynman diagrams for a totally general fan. So you don't, it's an interesting presentation, but it doesn't substantially differ from enumerating all the Feynman diagrams. And there's an extra magical thing. There are sort of three magical things in this story. This is the second one. And there's an extra magical thing that this fan is built out of simple pieces. And you can see it already in our simple example, that this kind of, this sort of fan can be thought of as sort of drawing three simpler things on top of each other. But in general, if we do endpoint, the endpoint tree amplitudes in this example, the number of cones of this fan is the number of Feynman diagrams that grows exponentially with the number of particles. But the number of simple pieces that it's built of is simply the number of propagators. And so that grows like n squared and not 4 to the n. And that's highly non-trivial. It would not be true for a random fan, but it's true for this one, that you can sort of build this extremely exponentially complicated fan by refining, putting on top of each other, a much smaller number of ones. And that gives rise to these, I told you there are concrete formulas for amplitudes, and here are just two examples. I could show you higher loop examples as well with a little bit more notation, but this is in a totally self-contained way. All the tree amplitudes and all the one loop amplitudes, these are the amplitudes, not integrands, are given in terms of integrals over this an n-4 dimensional space and an n-1 dimensional space. But where the objects that show up inside these integrands have this interesting piecewise linear property that look like these interesting maxes that compare different linear expressions with each other. Okay, so all right, so that's I think all I will say about it, other than to say quickly, how is this picture related to what I was telling you about the icosahedron? And in a very precise sense, this fan is dual to the icosahedron. Okay, so if I took these pictures, not this one, but actually, if I took the thing that I told you that we discovered artisanally before, this picture, if I take all of the rays, all the normal vectors to the facets of that shape, they will exactly give us the rays that we got from this fan. And where do we get that fan from? Nothing other than just labeling the curves on the surface and projecting. Okay, so that's why there's no cleverness associated with that. It just sort of comes out of labeling. But the idea is that the normal vectors to the surface, the normal vectors to these polytopes are the rays of this fan. And if I take any vertex of this guy, there would be 3 rays in this example bounding that vertex. So a vertex, which remember a vertex was a given triangulation, a given Feynman diagram, a vertex of this polytope would correspond to a cone of this fan. Okay, so the high dimensional, the top dimensional objects of the fan are the 0-dimensional objects of the polytope and vice versa. Okay, so these fans are the duals to these polytopes. All right, I think that's all I will say. Let me just end. There's a lot more I could have said. I didn't say anything about the connection to strings or to counting problems. But anyway, I did not really intend to talk about all that today, unless you gave me another hour. Let me just end by saying that I think over the past decade, we have been seeing really concrete examples where the rules of locality and unitarity of space-time and quantum mechanics emerge from more elementary mathematical rubric. And there's a common theme of the story of amplituhedra that I didn't tell you anything about, and these newer surfacehedra and their duals. There's some notions of positivity, topology, and combinatorics that lives directly in this kinematic space. And remember, we started with a seemingly very boring, arid space of just n null momenta, or the dot products, but just enough structure went into them to associate them with curves on a surface. And that was just enough structure to label the curves, which then allows us to project, which brings the fans to life, which then starts the whole chain going from there. Okay? We've seen something similar before in the story of the amplituhedron, where it's even less. You really literally start with n four-dimensional vectors, but they're ordered in some way. That's the only thing you have. They're ordered in some way. It's the same notion of ordering. And that lets you ask certain questions about matrices that you would build out of them. You can ask for determinants made out of consecutive columns of that matrix to have fixed signs. That wouldn't make sense if they didn't have an ordering, but because you have an ordering, you can do it. The tiny bit of structure then lets you get going, but somehow it's these words. The words involve notions of positivity, topology, and combinatorics. Has just enough structure in it to allow you to ask questions that then, I think rather remarkably, have all the richness and complexity in them that you need to extract objects that you can interpret as amplitudes that are local and unitary. But we have a very, very long way to go, so you should really stay tuned. My own feeling is that as we get closer and closer to describing the real world, all aspects of the real world, not just in some approximations, we should really try to push to describe as much of reality as we can from this point of view. And I hope we'll see, and I suspect we'll see, and I fully expect to see, more and more magic as we get closer and closer to the real world, not less and less. And somehow that's been the experience so far, is that the very first set of objects involve gluons and maybe supersymmetric versions of them, and there are all kinds of excuses for why all this stuff was happening that had nothing to do with maybe very special properties or very special theories. Now we're talking about totally generic things that have nothing to do with supersymmetry, nothing to do with being in 4 dimensions. They're very, very general, basic facts about these kind of pictures of what propagation in space-time and the sort of factorization look like. And I have a feeling that there's something about this. There's something general about this, and the more and more we understand, hopefully the more and more of this grammar we'll learn, and the more and more of these rules we will begin to learn to talk about from this alternate point of view. But anyway, the proof will be in the pudding. So, and hopefully I'll be able to come back someday and we'll understand the principles well enough that I'll be able to give a proper length talk about these ideas without going on so long. So thank you very much.
Thank you very much for this wonderful talk. A lot of fun. Time for questions now. What's the microphones?
Hi, Nima. Is it working? Yes, good. Thank you for an excellent talk. Only question is, so when can we expect to see this on the archive and read about it?
Is one of my collaborators paying you to ask this question? No. Hopefully by the end of the summer. The last time similar questions were asked, the end of the summer turned to the end of 2 summers from then. But it won't be this time. These people have to get jobs, so soon.
Great, thanks for the great talk, Nima. So first, I should say I completely ascribe to your point of view of giving a completely fresh view of one phenomenon that we know well and one answer, and abandoning certain hardwired notions. But even in, yes, in this geometric approach, one still has to assume that there are some free particles at infinity.
Absolutely,
right?
yes.
This you cannot get rid of. This really defines your momenta and so on.
Yes, absolutely.
So there is, this we cannot get rid of at this basic level, right?
Yeah, that's right. Yeah, I totally agree, yes. But, you know, and by the way, I mean, since you're an expert, you're probably just setting me up to fail asking this question. But, you know, we could say all kinds of things that, oh, well, there's these auxiliary spaces, we hate them, we hate space-time, blah, blah, blah. And yet, in various ways of talking about things, there are other auxiliary spaces that make appearances, right? So I think for this, all I can say is consistency is the hobgoblin of mediocre minds. Okay, we're taking all of this as some sort of inspiration to try to think of it from some other point of view, but it seems impossible that there's just some totally non-redundant, we have to sort of change what kind of, I think it's really that this metaphor of trying to find a new grammar is really what we're after. We're not trying to replace the notion of language. We're trying to find a different kind of grammar. But yeah, clearly, in the end, we can't say we're talking about, we have to say what we're talking about, right? Where there are some functions of P1 through Pn, and again, as you know, and all the people working in the subject know even better than I do in most cases, that's the real joy, is that they're in the end of the day, blah, 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 there's some function of P1 through Pn, and you have to put up or shut up. You have to produce that function or shut up. So, yeah.
And maybe a more, not technical one, but okay, you presented very exciting things, yes, about your current research. At one slide, you had some like formula with two formulas for or three level amplitudes and one loop amplitudes.
Yes.
So this is in what, in biadjoint?
This is just in this trace phi cube theory. Okay. Yeah, that's right. Just in this trace phi cube, and if you look at them, you'll see again there's nothing that looks like sum over diagrams. Nothing that looks like a canonical form. What is this? This is, since you know what these words are, this is literally what you would mean by the dual amplituhedron for the trace phi cube theory. Okay, so since you've probably suffered through many talks of mine for 5 years where I said we should find the dual amplituhedron for n equals 4 gluons, for n equals 4 super Yang-Mills. And the big reason for doing it was this sort of fantasy that if we could find the dual amplituhedron for gluons, it would give us exactly this unified form of Schwinger parameterization, which would allow us to do the loop integrals and then go to strong coupling and see the emergence of strings in ADS. So the amplituhedron itself would be about gluons, and the dual amplituhedron would be about strings. That was the sort of fantasy. The problem was that we were obstructed because these amplituhedra are much fancier objects than polytopes. We don't know what their duals mean in general. We still don't know, even though we have all sorts of tantalizing hints that they exist. We clearly don't know exactly what they are. That's the only reason I started working on this stupid trace phi cube theory, is because once we realized they're associated with polytopes, I'm like, aha, at least in this case, I know what duals of polytopes are. And if we understand it properly, then maybe we could see if this fantasy holds any water. It took a while to figure out what the duals are. And it's this whole story of the fan and all this stuff that I was telling you about is really properly thinking about what the duals are. But in this case, it exactly does what you would have hoped it to do in n equals 4. The dual story gives you a kind of a stringy representation, but it's a sort of tropical form of the stringy representation of the amplitude. Not the particles, but the sort of tropical stringy form is what you get from the dual of the surfaceedra in this case. But that's, so you see, so this here, it's an n minus, like a tree level, it's an n minus 4 dimensional integral. That's a projectivization of an n minus 3 dimensional integral, which is the number of propagators. And those variables, those f's, are a function of these, those f's are like stand-ins for Schwinger parameters. But there are these piecewise linear functions which turn into Schwinger parameters for a given diagram in a given cone. That's the sense in which one integral unifies all the different diagrams together into a single object. This is a somewhat funny looking integral. It's hard to do this integral analytically without breaking it up into the regions where it's piecewise linear. If you break it up into the regions where it's piecewise linear, then you go back to doing the Feynman diagrams. If I do the same thing for the bottom case, that's literally the Schwinger parameterization of the loop, both the tree and the loop part at one loop. But you could also leave it like that if you just wanted to have the answer numerically. You could just Monte Carlo that integral, and it's very accurate. So there's something, and this also suggests that something interesting should happen in the large n limit, where n is a number of particles, and that somehow as a number of external particles goes to infinity, this presentation of the answer is maximally powerful compared to the standard one. You have this polynomial growth in the number of terms here versus the exponential growth of the number of diagrams that becomes like as extreme in the large n limit. So there's some kind of smoothing that we get in these formulas in the large n limit. There's some kind of smooth expression that looks like something like a one-dimensional path integral but with an unusual action associated with these formulas at infinite n. So I think that's probably something interesting to be explored. That's not a limit where, in thinking about amplitudes, we've thought about that much. Does anything nice happen in the limit of infinitely many particles? Partially because we think there's no access to it. Well, this is a formalism that really gives us some access to it.
Thanks a lot.
Does anything qualitatively change about all of this when you do it for particles of different spin? Like I think you did it for scalars. But
yeah.
On one of the slides, there was something about
yes. So I'll just say something about it. It's something that, of course, we're starting to look at now. And what I can say, well, first of all, we know in a different setting of gluons and 4 dimensions and so on, there is something that happens, and that's the story of the amplituhedron. Okay, but it's in a somewhat different language. There's a very specific sense in which, I didn't tell you anything about the amplitude in this talk, but there's a very specific sense in which these polytopes that I talked about today, especially these tree-level polytopes, these icosahedron, somehow these amplituhedra are much richer, much more interesting, more primitive, deeper, but more unfamiliar objects than their polytopal cousins. So the icosahedron clearly lives inside the amplituhedron in some sense that we're beginning to see precisely, but there clearly lives inside it in some sense. On the other hand, we don't know how to generalize the story of gluons and the amplituhedron beyond the planar limit, for a completely general general number of colors. On the other hand, on the left-hand side, we've generalized this beyond the planar of all orders. Okay, so this is a totally all order statement. So the fact that the guy underneath exists sort of strongly suggests that it has to have its amplituhedronic friend on the right-hand side to make this diagram make sense. So that's one indication that something should happen when you have polarizations. But staying in this world of purely in this world of ideas, what you can do, I didn't have time to explain this in detail, but you can really imagine that you take, already in this phi cubed example, you take diagram, 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 and I told you that you can think of each one as actually coming from some unified object over the entire space that in every cone of the fan gives us the answer we get from the diagram here, right? In each region. And then the claim is that something beautiful happens that even though naively you would think it takes exponential amount of work to specify what that function looks like, you can do it in terms of these very simple functions. I didn't explain what the word tropical means, but they're so-called tropical functions, these functions that look like they have these maxes. Well, you can just experimentally explore whether that continues to be the case when you add polarization vectors. You start talking about spin. And so we've been doing it, and the early indications are definitely encouraging. So you put in polarizations. Now there's numerators everywhere, but once again, you would think the numerators take some random value different in cone to cone to cone to cone to cone, but it looks like when you look at it appropriately, they're also simple tropical functions that are built out of simple pieces. So that's a very concrete thing that you can start playing with.
Do you think same sort of properties would hold for theories with phi n interactions?
Right. Great question. Yes. There's actually there's been some very nice work from various groups in India around Alok Ladha and friends that have essentially talked about, and there's a very natural way in which you might think, for example, phi to the 4. Phi to the 4 actually live inside the phi cubed theory. So there's actually a way of engineering phi to the 4 from phi cubed if you imagine that you really made, you had a cubic interaction, but with some intermediate guys who were very massive. So that's a very simple way in which you can take the icosahedron and kind of move it around, rescale it, move it around, and discover some geometry associated with phi to the 4 theory inside it. Alok and friends recently put out a paper where they really systematized this and related ideas And I'm trying to understand them better, but their claim is that beginning with the sort of master icosahedron, all you've got to do is move it around and rescale it, and you can get any theory for phi to the p for any p. But it's not, I mean, it's very interesting. I'd like to understand it better, but it's not shocking a priori, because again, the singularities are totally universal. Any theory has these singularities, right? You might lose some of them, but you won't gain any more of them. So that's why that's the sense in which there is something universal about this structure.
More questions? I have one. Is there anything here that tells us why we live in 4 dimensions? Assuming we do.
Here, no. Here, no. Yeah, there's a lot here which is not cool. I mean, for one thing, when I say any d, I really mean d equals infinity, because I'm just assuming that all these Mandelslams are just independent, right? Whereas we know that ultimately there are relations between d vector. Anyway, so those Graham determinant conditions and so on we don't see here. We know from other points of view that extra magic happens in 4 dimensions and on-shell conditions, little group, blah blah, spinor helicity variables, blah blah. So special things should happen in 3, 4, 6, and 10 dimensions for all the usual reasons we know and love. And yeah, this is sort of blind to all of that. And yeah, so and also maybe the most basic difference between this geometry and the amplituhedron, and the reason this is less interesting than the amplituhedron, is that here the basic objects are already pairs, right? It's like pi.pj. They're Mandelslams, right? It's a super old-fashioned way of thinking about what kinematics are. If we learned anything from thinking about amplitudes, starting 30 years ago, is that you should not do that, okay? And you should not work with polarization vectors that suck, and so on, right? So that so somehow, yeah, this is a much more this is a much more old-fashioned it's a much more old-fashioned perspective from that point of view. But I should say this. I mean, I think if you're a string theorist, it should bug you a little, because there is a real tension here. That string theory is the greatest S-matrix theory of all time. And yet the way string theory thinks about spin is the way dumb field theory thinks about spin. You have polarization vectors, gauge redundancy, and so on. It has that same very kind of, from the on-shell perspective, this very field-centered, old-fashioned point of view about how to think about spin. So yeah, so that's a real tension. But this thing, as you see, is associated with surfaces, and is, I didn't have a chance to explain it, but is achingly close to strings. Okay, so but it has the same sort of basic tension in comparison to the I think things that are a little more interesting in at least the way they think about the kinematics, directly in terms of momenta or twisters or whatever you want, but directly one variable per particle rather than these things that involve pairs of particles.
How would you envisage describing QCD in this sort of language? Because in that case, you don't have asymptotic states, and you have probably. You
mean with real QCD, with confinement and so on? Yeah, right. Wonderful question. I think I mean this is you're asking. You know full well how hard the question is that you're asking, but anyway, I will answer it. I will tell you how far we are from answering it anyway, even though you know better than I do. But one of the real complaints about this entire, a totally legitimate complaint about this entire subject, whether it be this or almost anything else which is done in this neighborhood, with the notable exception of some of the things that you've done, is that so much of what we do in amplitudes is perturbative. And people say, oh, why the heck are you wasting your time on these silly perturbative things? There's so many fascinating non-perturbative phenomena in field theory, and you can do the conformal bootstrap, you can do this and that, we can do all these fantastic non-perturbative things. Why are you wasting your time with these silly things in perturbation theory? And I would say, well, you have to walk before you can run. And trying to do non-perturbative scattering amplitudes is like trying to do GR without knowing linear algebra. So we have to, the point is, it's not a technical point. There is a big physical deep difference between the questions we ask in amplitudes and the questions where we are much further along in giving non-perturbative answers. When we talk about properties of Euclidean conformal field theories, the key word is Euclidean. So it's perfectly well defined. It's Euclidean. We understand so much about it. We can specify ahead of time what kind of functions show up, what the properties have got to be. If someone hands you a list of purported things that satisfy all the axioms of Euclidean conformal field theory, you can check if they're right or wrong. But that's a big difference with amplitudes, because we don't know. I think it's an embarrassment, but that we don't know in the 21st century what are the rules if someone hands you a scattering amplitude. How do you check if it's right or wrong? We don't know the rules. And the big difference is that it's not Euclidean. We have a much richer pattern of singularities. It has to do with the averaging phases. It's about dynamics. It's about time evolution. And so it's that very basic question, how is causality encoded in these boundary observables? We still don't know the answer to that question. It's a physical question. Clearly has a very deep and some deep mathematical structure to the answer to this question. And we don't know the answer yet. And that's why we can't ask these non-perturbative questions yet. We don't even know the answer in perturbation theory. We've known the answer at one loop for a long time. We don't even know the answer at two loops in perturbation theory yet. So I think the attitude, and that's the sense in which what we're doing here is different than the S-matrix program, is that the S-matrix program of the 1960s sort of hoped that you could put on your responsible cap and derive the analytic properties of the S-matrix somehow from the top down, and they couldn't do it. That's why all the old books had to sort of cheat by staring at Feynman diagrams and pretending that they didn't in order to see what the analytic properties were, and they didn't get anywhere. And so the hope today is not that we're going to repeat the same process and this time get it, I think. At least that's not my hope. My hope is that we're just going to guess the right answer. We're just going to guess structures that sort of give us the answer and then learn to read the rules out backwards from how the answer presents itself. But that's why we can't even start asking the kind of question that you're asking yet. I realize that this is, it's very dangerous when someone says we have to understand 7 things before we get to a physically very interesting question. So it's reasonable to be skeptical. I'm skeptical sometimes myself. But on the other hand, there's part of nature which is QED. There's part of nature which is gravitational wave scattering. And there we don't understand. There are things about the real world that we don't understand. And it seems to me that if we find some sort of deeper understanding for how causality is encoded in the scattering amplitudes, that would be a revolution. And then maybe the way to even approach the question of how to deal with confinement and so on would present itself in a way that we can't understand now. I understand it's a very unsatisfying answer, but that's the best I can do.
Hey, are cluster algebras still a key player in this framework?
Yeah, cluster algebras have been a very key player. Sort of amusingly, it took us a year it was so key that we were addicted to them a long time, and they're not quite right. Almost exactly right, but not quite right. And it took us a while to realize they're not quite right, but they're very close. So probably at the level of the question you're about to ask, yes. The thing which is somewhat more fundamental are these categories of quiver representation. So quiver representation theory is definitely absolutely key and fundamental. But the sort of connection to cluster algebras, and there are some little annoying things very, very early on. Something that you learn in this, at least in the more mathematical side of this subject, something that mathematicians appreciate, but at least, normal physicists, like non-mathematical physicists like me, don't appreciate, or don't naturally appreciate, but I'm appreciating now, is that, physicists are happy with things not always working. Because physics always is filled with things that always have little counterexamples. Oh, there's some infrared divergence. Oh, you blame something. But But you know, when there's a mathematical structure, it has to be perfect, right? So either there's a connection or there isn't. And if you're ready to make a connection to some mathematical structure, you can't be screwing around at that point. It's going to work or it's not going to work. And that's one of the most fundamental things that we know about amplitudes, that everything gets reduced down to 3-particle amplitudes, and they're the most basic thing. And that's a very annoying thing about cluster algebras early on, is that they say, oh, there's a cluster algebra associated with every surface except these teeny tiny special cases, which are exactly the ones which you have to talk about if you want to blow all the way down to 3-particle amplitudes. So it sort of hurt me, you know, very early on. Damn it, we can't quite do it, can't quite do it. On the other hand, we really need these cluster guys. And so it's not quite right. And the actual completely correct thing is I mean, what the cluster algebra of surfaces people do is perfectly natural if you like cluster algebras, but it's not natural if you like this physics.
Other questions? So far, we've only had questions from researchers, so uninitiated people.
Hello, I hope this is such a simple question that it's meaningless, but I was terribly impressed at the beginning when you said quantum mechanics realized that the principle of least action took over from the notion of energy and particles. What's your equivalent now? Is this basic that you're working on geometry and maybe topology or something like that?
I mean, that's the rough analogy. Unfortunately, anyone who knows anything about the history of physics knows that you can choose examples to illustrate any polemical point you want to make. Okay, so I'm trying to illustrate a particular polemical point, and so I give this particular analogy. I could easily construct analogies that would illustrate the opposite polemical point. That's the problem with knowing the history of physics well. But anyway, the polemical point that I wanted to make is that the coming of the quantum revolution was sitting there in a structure seen in classical mechanics, right? And it could have bothered people. It did bother people, in fact. De Maupertuis and Euler and Lagrange and friends who discovered the principle of least action. They discovered the principle of least action, and it bothered them that there was this strange way of talking about classical mechanics that didn't seem deterministic. And there are these words, this teleological way of talking about classical physics. Again, the particle sniffing out every path it could take from A to B and so on. Why is there this other way of talking about classical mechanics? The formulas end up being exactly the same as Newton's laws, but why is there this other way of talking about classical mechanics? Back then, they didn't know the answer. It bothered them. They didn't know the answer, and today we know the answer. We know the second way of talking about classical mechanics exists because the world is quantum mechanical. And the way quantum mechanics reduces to classical physics is not to reduce to F equals ma. How could it? You can't go from being deterministic, non-deterministic to being deterministic. You can't be a little non-deterministic. It's like being a little pregnant. But it had to reduce to a way of talking about classical physics where determinism was secondary and not fundamental. Okay, so that's the historical point that I was trying to illustrate. And I'm saying the analog today is, it seems, how could we possibly describe particle scattering or other simple, ordinary physical processes without space-time and without evolution in Hilbert space? They're the entire point. They're the entire framework we have. So, but we should try to learn to naively tie our hands behind our back and do it another way, okay? Now, the sort of fun of it is that not only does it end up not being tying your hands behind your back, but it's giving you 10 hands. So because the answers are so much more simple when you see them from this point of view. Okay, but the sort of hope is, but we're not yet at a point where we have this sort of simple principle, like, oh, it's a principle of least action. We're just, scratching away and finding a few examples here or there where we can see something like this work. And so we've been working on it for 10 years, and we have a few things to show for our efforts. And I don't know what I don't think we know the end point of this process. It could be these are all many red herrings, and they're just little exceptional things that describe this, that, or the other. It could be that they're like they're pieces of some larger continent of ideas that we don't yet know how they're connected to the rest of physics we understand well. What's clear is that they're not easily continuously connected to the rest of things we understand in physics well. They're clearly different beasts. Whether they're whole sort of continents or just little isolated things, we just don't know yet.
Thank you.
back to the idea of doing this for particles of higher spins, to even be able to do that at all and to start thinking about spins as like representations of space-time symmetries, aren't you kind of forced to then insert like, space-time stuff into this whole thing and you wouldn't have space-time emerge anymore?
Yeah, I think that this is maybe a little bit related to Jürgen's question. Kind of. I mean, if we describe spin with polarization vectors, to me, I'm already unhappy. Okay, because already it's something not quite. It has a feeling of there is a field that you're putting on shell and it has to have some gauge redundancy on it. So not. Anyway, but so it's not philosophically perfect from this point of view. On the other hand, somehow, as I said, we can't get too wedded to what we want the answer to look like, because again, the greatest S-matrix theory of all time is string theory, and that's the way string theory thinks about spin. So whatever our prejudices are, we should, I remember I had a big, my friend Freddie Gacciazzo and I would sort of trash polarization vectors all the time. It was lots of fun and learning, well, polarization vectors suck, they're the worst things ever. And then he wrote these beautiful papers using polarization vectors, and he alerted me to the papers by sending an email and saying, Nima, I'm very, very sorry. Okay, I'm very, very, very sorry, but, and then, okay, there are these fantastic formulas with polarization vectors. I'm like, damn you. You know, you're like telling me, agreeing with me that polarization vector sucks, and then behind the scenes, you're like screwing around with polarization vectors. So I think, you know, so I'm not too principled. That's why I was saying, you know, we can't be too principled. Consistency is a hobgoblin of mediocre minds at the moment in the development of the subject. But I somehow hope that we'll get rid of the polarization vectors in the end.
Thanks. Possibly an unfair question, but what do these theories about polyhedra tell us about space-time? What restrictions are there? What hints through the fog?
Well, I mean, I think what I would say so far is that they're just a way of capturing properties of the answer, which we normally ascribe to the presence of a locality in space-time and unitary evolution in Hilbert space. If I repeat the philosophy of this talk for the umpteenth plus 1th time in the answer to your question, in the end of the day, there's a bunch of functions. You're a very practical person, you're an experimenter, there's a bunch of functions, you measure them. You don't measure them directly, you measure their squares, mod squares. But imagine you could measure them directly. There's just a bunch of functions. All the rest of the stuff, they're just measuring these things. To them, it's just like blah, 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 theorist, blah, 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 theorist. Okay, so there's a bunch of functions. But the functions are interesting. They're not trivial functions. They're not like a plus 2b, right? They're very interesting functions. They have sort of interesting singularities. They have some interesting patterns in them. And that's why I was telling the story in this way. The experimenters might notice some of these patterns and then present the talk at a conference. This is the outside space-time conference, because none of these theorists live inside space-time. They're just seeing the results of these experiments. And then one of them is named Feynman in the audience. So I know what's going on. What's going on is Feynman diagrams that I just named after me right now, right? That's what's giving rise to these interesting singularities. There's virtual particles in the intermediate. This space-time is really cool. You draw these pictures, things go on in the intermediate of the space-time. That's responsible for generating the interesting structure in these functions, okay? And that's one of the mistakes we sometimes make in physics, is we tend to reify the formalism that produces the answers, especially when the formalism is general and powerful. Right? You start, you know, confusing the formalism for getting the answer with what's quote unquote actually going on. And that's really happened in this context, so much so that, you know, when we teach things, we say, oh, there's these virtual particles, the vacuum is roiling with particles and antiparticles. Oh, this is all part of a formalism for doing the calculation. You don't actually see it in the answer, right? You know, so, but the point is the answer is rich and has lots of interesting properties. And we understand enough about what those properties are to be able to point to say, that property, that came from locality in space-time. We can interpret that one as coming from locality in space-time. We can interpret this one as having to do with unitarity, quantum mechanical unitarity. And by the way, it's very interesting that the two things that I'm pointing to are in the same spot. They're not, well, there's the space-time part, there's the quantum part. It's just the same thing. The sort of singularity of the function simultaneously encodes the properties that make it look like it comes from local interactions in space-time and unitary evolution in Hilbert space. So the idea here is to sort of produce those rich functions from another place as an answer to a different question. And I didn't actually tell you in the talk quite what the question was. I sort of told you the beginnings of, say, you draw these, you produce these polytopes, but there are certain objects you associate with these polytopes. They're the things that we call canonical forms. There are differential forms that have prescribed kinds of singularities on the boundaries of these polytopes. They're very natural mathematical objects, what you would think of if you just played with these polytopes. And those turn out to be the amplitudes. Okay, so you have an object, and there's a question you ask of the object that gives you the same set of functions, totally different set of words for what calculates it, but in the end, exactly the same set of functions. So that's all we've learned so far. Even in these baby examples, that's all we've learned so far. We have not changed the thing. We're talking about exactly the same physics, but from this different point of view. There is this now fantasy, and I stress it's a pure fantasy at this point. And that's this polemic story that perhaps if we understand this way of talking about things, and if we understand it well, it will tell us how to sort of release the sort of vice grip of space-time and quantum mechanics in our thinking and tell us how to generalize beyond it. That's the analogy. You might somehow imagine if you had the principle of least action, you might imagine building something like a path integral, starting from something like that. Even though that's not the way history happened. You might imagine doing something like that. You at least be in the correct headspace to imagine doing something like that.
I saw a hand somewhere there. It's time for one last quick question.
Thanks for a very interesting talk. So since you mentioned about n going to infinity, I remember this result by Rubakov about, yeah.
Wonderful question. This is exactly something I hope can be settled from this. Yes, yeah. So there are these fascinating Russian papers from the late 80s and early 90s that exactly had some interesting puzzles about the large n behavior. And I suspect that could in principle be settled from this kind of formalism. Yeah. Should I explain what your question was? Maybe you can explain it to everyone else. So yes. Yeah, there's some papers by Rubakov and maybe Voloshin. I can't remember all the sets of people, but there's this old question of whether the factorial growth in Feynman diagrams means that the amplitudes for a sufficiently large number of particles actually grows. Okay, because you have something like g to the n, but the number of diagrams goes like n factorial. So for n of order 1 over g, 1 over alpha, you might expect that the amplitude becomes unsuppressed again. And there's this whole sort of question of whether that's true. By counting, it seems like it might be true, but then it seems like physically ridiculous. But then these people did a calculation for what the n to n amplitude looks like right on threshold. So you imagine you have n to n, maybe that's not quite what they did, but it's something close to this. If you have n to n, but the particles are exactly on threshold, because they're exactly on threshold, all the spatial momenta are 0, and so the problem only depends on time, and so you can reduce it to solving just the classical field theory problem just in one time dimension, and you can just solve that problem and get the amplitude from it and exactly see this factorial growth there in the answer. So it seemed to be there is factorial growth in the answer in this limit. And then people said, oh, but that's very special to this limit. The second you go beyond threshold and allow general angles, that should all go away. But that's kind of where it's stuck for a long time. There are people trying to numerically simulate it. They go back and forth. Some people say it's a motivation for building a 100 TeV collider because you might be able to sort of produce sphalerons. Anyway, Volodya Jose has some very interesting things to say about this. But anyway, it's a question that's been laying around for a long time that has not been answered. And it's on our to-do list to look at it from this point of view, for sure.
Okay, so, well, Nima, thank you very much for this wonderful evening and to everyone for coming here today.